Welcome to Chapter 5, Industrial Applications of Bayesian Optimization. In this final chapter, we move from theory to practice, exploring how Bayesian optimization solves real-world process optimization challenges. Through 7 detailed case studies covering chemical reactors, catalyst design, pharmaceutical manufacturing, and more, you'll see how this powerful technique reduces experimental costs by 70–80% while achieving significant performance improvements. We'll cover 7 progressively complex case studies in this chapter. These range from continuous stirred tank reactor optimization with temperature and pressure control to 4-element catalyst composition design to 6-parameter pharmaceutical process tuning. We'll also explore quality optimization under GMP constraints, energy minimization with Pareto analysis, 3-objective optimization balancing yield, quality, and cost, and finally a fully integrated polymer polymerization workflow. The key insight is that Bayesian optimization typically requires only 30–50 experiments compared to 150 or more with conventional design of experiments. Our first case study focuses on optimizing an esterification reaction in a continuous stirred tank reactor. We optimize 3 parameters: temperature from 60 to 120 degrees Celsius, residence time from 10 to 60 minutes, and catalyst concentration from 0.1 to 2 moles per liter. The key challenge is maximizing yield while respecting safety constraints, keeping temperature below 110 degrees and side reaction rate below 5%. Using constrained Bayesian optimization with probability of feasibility, we lifted the yield from 85% to 94%, a 9 percentage point gain in just 30 experiments compared to 150 with traditional DOE, representing an 80% cost reduction. Case Study 2 tackles multi-element catalyst optimization for CO2 reduction reactions. We explore the composition space of 4 elements: copper, zinc, aluminum, and manganese, each constrained between 10% and 50%, with the total summing to 100%. This simplex constraint creates a tetrahedral feasible region in parameter space. The optimization revealed synergistic effects between copper and zinc, leading to a 51% improvement in catalytic activity from 320 to 485 micromoles per gram per hour, while maintaining 75% co-selectivity. All this was achieved in just 45 experiments from a theoretical search space of over 10,000 combinations. In this pharmaceutical synthesis case study, we fine-tuned 6 process parameters simultaneously: temperature, pH, agitation speed, reagent ratio, catalyst concentration, and reaction time. The Gaussian process models the complex interactions between these parameters, with the surface visualization showing how uncertainty decreases as we gather more data. A classical response surface design, such as Boxbanken, fixes the whole experiment grid in advance, whereas Bayesian optimization adapts each new run to what has already been measured, while tracking multiple quality metrics including yield, purity, and impurity levels. This demonstrates how BO handles high-dimensional optimization efficiently. Pharmaceutical manufacturing requires strict compliance with good manufacturing practice specifications. In this case, we optimize throughput while satisfying 4 hard constraints: assay between 95% and 105%, impurity A below 0.5%, impurity B below 0.3%, and dissolution above 80%. The probability of feasibility approach guides exploration intelligently, preferring regions likely to meet all specifications. This constrained optimization demonstrates how Bayesian optimization can maximize production efficiency while never compromising on safety or quality requirements. This case study addresses the fundamental trade-off between productivity and energy consumption in industrial processes. We optimize temperature, flow rate, and recycle ratio to find the Pareto front, which represents the set of solutions where improving one objective necessarily worsens the other. The gray points show all evaluated experiments, while the red stars connected by the dashed line mark the Pareto optimal solutions. This visualization enables informed decision-making based on current energy costs versus production targets, with solutions ranging from high productivity to minimum energy consumption. Real industrial problems often involve more than two objectives. Here we simultaneously optimize yield, quality, and cost, where we want to maximize the first two while minimizing the third. Using scalarization with varying weights, we approximate the three-dimensional Pareto surface. The radar chart helps visualize how different solutions perform across all objectives, enabling stakeholders to select solutions matching their priorities. Expected hypervolume improvement, or EHVI, provides a principled way to balance exploration across all objectives during the optimization. Our final case study demonstrates a complete industrial implementation for polymer polymerization. We optimize 7 parameters to minimize polydispersity index while achieving at least 90% yield, subject to constraints on temperature, viscosity, and residual monomer. The optimization cycle begins with latent hypercube sampling for initial coverage, builds Gaussian process models, computes constrained expected improvement, executes experiments, and updates. In 75 experiments, we achieved a 36% improvement in PDI from 2.1 to 1.35, with 92.5% yield, compared to over 300 experiments conventionally, representing a 75% cost reduction. Congratulations on completing this chapter on industrial applications of Bayesian optimization. The key learnings include understanding real process complexity with multi-objective constraints, adopting a stepwise approach from simple to complex problems, implementing reliable constraint handling for safety and quality, using Pareto analysis for multi-objective decisions, and achieving 70–80% experimental reduction with 30–50% performance gains. For successful implementation, follow these best practices. Formulate the problem clearly with defined objectives and constraints, use latent hypercube for initial sampling, select appropriate acquisition functions, prioritize constraint compliance, target convergence in 30–50 iterations, and verify results with multiple confirmation experiments. You are now ready to apply Bayesian optimization to your own processes.